just allow people to get in.
Yeah, I usually babble.
I saw him in the cafeteria, and I just gave him a hug, and I figured that I wasn't sure that was a good thing.
Oh, he's so funny. Well, he has the same reaction I have. But then he like, you know, like I don't want to hold on to him until it's for me.
I didn't do that.
Yeah. Yeah. We're all still, we're all still, yeah. Like happy family. All right. I'll look forward to the announcements for the next time. I'll announce what I haven't posted yet. Amit did not give me bio and but I have to say oh, no, right. Okay. Okay, hi everybody. Let's talk. Hello, good evening. Hi. Hi there. Oh, you're so cute. You're passing them up. So, welcome to your advanced session of the SFBay meetings. As you know, I'm with that's Lena. Is poodling around here somewhere, and Sean is important. He's running the user group important tonight. So, we go on global. I don't even know. So I'll tell Sean about half the people we had last time because he's not here. Apparently, that's a big he might be checking us out on Hangout, so we'll try to say nice things. So we're going to continue our OpenStack networking month tonight. We have the good folks from HomeGrid here to enlighten us with a really interesting topic. I got pretty excited about this when I ran into my old manager, Wendy Cartier, at the Silicon Valley Meetup user group meeting conference a couple of weeks ago, a month ago, I guess exactly. And we brainstormed about cool things that they could come and present, and came up with this topic, and with the help from her team. And so really excited to have us here. So Sharad is going to be your main presenter, and Ziraj? Is that right? Okay. He's going to be the one running around tonight with the microphone. He's going to also be helping me answer questions. And after a year and a half into this, I finally learned that format will work better than me running around with the microphone. Justin, hi. Good to see you. Okay, so want to continue on sort of on the theme and the meetup after that, which will be October 1st, because we're first and third Thursday of the month, as you guys are well aware. So the October 1st meetup, we're going to do something. We're going to one of our colleagues in NFV was working on starting the Open NFV user group, and so to kick it off, we thought, well, let's combine our user groups and let's do an OpenStack carrier grade OpenStack meetup, because we've been getting a lot of questions about how to make OpenStack carrier grade, how to make it truly 5, 6, 9 stack scalable, all of that stuff. So we've asked one of the folks from NFV to come and enlighten you all on that topic. I haven't posted that on the Meetup group yet, but I will maybe even tonight. But anyway, that's what's happening on October 1st. So NFV in the house at that point, OpenStack carrier grade, and it should be a really interesting topic. I have decided, unless Rick has decided, so the October 17th, I think, is the next one. I'm not doing that math right. 15th. So the 15th, I don't have a speaker yet. So if anyone has anything they're dying to say to this user group, let me know. and we can maybe work something out, or let Rick know, or let Sean know, or let Lena know. So as per request, I'm sure we have tons of pepperoni pizza. Did we get it? It was like anarchy last time because we didn't have pepperoni pizza. We're all got eaten first, or I don't really remember what happened. But my point that I'm getting at is that if you guys have any special requests, not that pepperoni pizza has to be a special request, but if you do have any special requests for dietary needs, and you are a regular, or at least you can promise us that you will be at the next meetup, that we are going to be fulfilling your special request, we will be more than happy to do that. For instance, these nice folks scale the ends of the earth to find me here, which is so cute and a nice ice tub for me. So if any of the rest of you guys are gluten-free or something like that, then let us know. She usually serves out a gluten-free pizza for me, so if there's any other, is Rocky today? Nope.
How about old corn beer?
I think you requested that before. I actually looked for that here and I could not find it. And I really looked, and so I'm pretty sure it exists. But we do try to honor special requests. And I will, one caveat, if you are truly gluten-free, like if you are as sensitive as me, it's a little game of roulette. I usually eat the pizza because I'm usually starving by this time of day, but half the time it fights me back. So I think cross-contamination, all that stuff, it's kind of hard to get a pizza place to really be gluten-free. So just fair warning, we can't really vouch for vendors. So all caveats aside, I think those are my only announcements. Oh, fun stuff. Okay, you know I like to give you guys free stuff. I brought the copies of the book, Intro to OpenStack book. That's not what it's called, but that's kind of what it is. For anyone that you guys are all in the advanced session and you all had this book before. In fact, I saw some of you reading it last time while I was trying to go through his slides, and I think that young man over there actually finished it before Sean finished his slides. Anyway, go ahead and give a copy there if you don't have one already and you would like one. You can also download it off hpress.com. And I brought some little pins. Okay, so we did this for the OpenStack. No, we did this for Cloud Foundry Summit. We did them in sticker form for the summit that was here. And then we did the pins for the summit that is going to be in Europe in a couple of weeks. And they're developer languages. There's no branding on them except for the developer languages. It's very hard to read. They're tiny and thin form. In sticker form, they're a little bit easier. Got a couple of them on the back of my laptop. So we've got Ruby on Rails and Java and Node.js. We've got Python, your language, OpenStack, Java. We can OpenStack now. No matter what the bylaws say. And a couple of other, I think, Go, .NET. So if you are a developer and you have a language, a favorite language, you can sort through and grab a pin. And if we're all out of that one particular one, I can run it through if I'm feeling in the giving vein. Okay, all right, Sharad. So I think we've got all enough. I think the last bus has arrived. So as people trickle in, I guess we're gonna have a lot of pizza. So you never really know. Last time it was like out the wire. So your mic is, oh, you got it? Is it on? Did you test it? Can you hear him?
Let's see. Sorry about that.
I suspect that's not what you're going to be doing in your presentation. So why don't you talk?
I need to have it closer?
Yeah.
Okay. So maybe
You know, while he's doing that, I have a question for you guys. As I browse topics for this fabulous meeting, I'm thinking of having our good friends who focus on interesting things like containers come and maybe do a presentation on containers and OpenStack. That's something you guys would be interested in.
Yeah,
Sure.
it's the best.
So you have containers and OpenStack. Okay.
Or there are like these ones here, I don't know.
Oh, yeah. Yeah, let's turn it on first.
To know that stuff will be over.
When you get to Meetup,
I mean, like, set. Oh, yeah, we
Should set up.
haven't, but,
Wow.
okay,
Really?
set. Yeah, okay. As it applies to OpenStack.
Should
Okay, this is the OpenStack.
There's something for this reason.
But yes,
This has,
probably.
they have this like this.
And can you email me with that request?
No, I
And
think
you
this
know
is for the
that
settings.
you
So
have
I
to
guess
bring
this
that
should
so
not
that
be.
so that's just off the top of my head and.
There we go. Give me that so I can toss them.
Yeah. Yeah, well, okay, we'll think on that one. Well,
Sorry, when I tested it earlier, it was working.
so
Maybe it's just died.
Yeah.
I guess that's what it is.
And we'll work on that, and any other topics that you guys have, but I am gonna work on the containers
Oh,
one, because it would be, it would be interesting for me to participate in as well. So, okay, did we get that one?
I think we just have to change the battery up.
And we got that working, that sounds good, can you guys hear?
All right.
Okay, and I'm gonna go to your off the other mic, so you can run around and let the crazy person with questions. And maybe they like to make it interactive, I don't know, is this your first time you guys have come, or have you come before to?
So this particular meetup,
Okay.
for me at least.
Yeah,
but I
so
think
they're not shy, especially
That's-
after a beer or two, so they'll probably interrupt you and ask questions.
Thank you.
You might want to raise the.
Wait, does he respond or do we respond? I think, yeah, just turn it on.
All right. So again, thank you everybody for coming here on a Thursday evening. Really appreciate it. And it's a small audience, so I think we can definitely make it very interactive. My objective here is to present multi-hypervisor solution. That's what the agenda says, and we talk about also about the technology. Any questions, anytime, please feel free to ask as they come to your mind, right? I think, as I said, from an audience point of view, I think we are a very good size to have a very interactive session. So I'm hoping I can make your time here productive, and we find this a useful use for your time. All right. So again, my name is Sharad Alawat. I'm heading the field engineering and the professional services team. So as part of field engineering, what we really do is work with different technologies and figure out how to integrate them and try and do some initial prototyping of solutions. And as those solutions start getting some traction, we then take that solution into a more prioritization type of a format. So I do want to sort of ask a question up front so that we don't end up spending time on standard neutron type slides. I mean, this was an advanced OpenStack meetup, but is everybody very familiar with just the basics and the fundamentals of neutron networking, right? So, okay, good. So I've got 3-4 slides, so I can easily flip through them very fast. Okay, so OpenStack, everybody understands what it is: open source cloud operating system, many different versions out there. Neutron started off in the Folsom release, right? It's essentially for providing networking services. Before that, the focus was more around compute and a little bit of storage. And then they figured out that, yes, we got virtualized compute, but it needs to be able to interact with other virtual instances, and we need a little bit of flexibility there. So that's when the concept came out for Neutron. Essentially, a set of REST APIs. From a design point of view, it was created in a modular framework. So it's extensible, and it has enough flexibility in it where you have a standard set of core APIs, and then for additional functionality, you can always extend those APIs, and you can also have extended services and everything else, right? So again, I'm pretty sure everybody here is very familiar with these components of Neutron. One of the key things where sometimes there's a little bit of confusion, Neutron is not designed to implement the network itself. It is just a set of APIs. There is sometimes this statement like, integrated with OVS and network node solution, and then people start calling that Neutron. That's not sort of actually Neutron. The implementation of the networking infrastructure, which is sitting under this set of APIs, I mean, it can be thick or thin, essentially saying that you can have Neutron plugins and solutions which can be very limited in sort of the functionality they offer, or they can be very extensive and give a very feature-rich set of services and everything else, right? So there are many different solutions out there, and they have different capabilities. Okay, so essentially, again, it's the whole concept of plugins to give you the extensibility and be able to keep on allowing the user community to sort of try out and experiment with different networking component technologies which they may want to sort of try and use in an extensible manner. Okay. In terms of the architecture for Neutron and OVS, I mean, when you kind of think about it, you basically have the ML2 or the OVS plugins. You've got the various different compute nodes. You've got agents on those compute nodes, and all your L3, L4, L7 type of services are all sitting on the network nodes, right? So that's kind of the standard sort of thing which we have as OVS plus the network node type of solution, which is out of the box your Neutron standard solution from OpenStack, right? It's along the same lines. And so essentially with this thing, you have some fundamental issues with that type of a design in terms of how you need to really take into consideration how many tenants you're going to have, how many compute nodes you're going to have. You have to sort of figure out how the traffic workflow is going to be, and essentially around your L3, L7 sort of services, you really have to figure out how you're going to scale them based on how the traffic is going to hairpin through those services. So OpenStack networking and plum grid. So essentially, standard OpenStack block diagram, you got the virtual compute, you got virtual storage, and what plum grid focuses and specializes in is networking. We are a core networking company. We have focused on building out a full extensible network platform. And that's what we'll just have a few slides on that. So when I say it's a platform, it's not just a set of scripts or a set of tools which are sort of stitching together some of the networking sort of features or the networking capabilities which you need in making virtual machines come together and talk to each other. It's a platform where you actually have the concepts of bridges, routers, DNS, NAT services. You've got DHCP services. So it's a full-fledged standalone sort of a platform which we have gone ahead and used to provide the networking services for OpenStack. So if you talk about the various different building blocks of the plum grid platform, the platform itself consists of a cluster of directors, gateways, and edges. If you've got these as the compute nodes or the physical servers, on each of these physical servers, which is a compute node, we end up with a Hypervisor edge. We have various different gateway form factors. We can do generic x86 boxes or specialized accelerated VTEP gateways like Aristas or Cumulus. So we can integrate with various different options when you go north, south, or east-west in terms of the VTEP termination points. And the directors themselves are deployed in a odd number of nodes. So you can have 3 or 5, where the whole idea being that it's a HA cluster, so all these services and everything else are operating in a highly available fashion. So now let's just take a quick look at some of these components in a little bit of detail. So I did mention Hypervisor. So what is the Hypervisor? So the Hypervisor, I mean, it is a key building block for the plum grid platform. The plum grid platform, again and again I'm using that word, it's not, as I said, an orchestration around OVS. we do not use the OVS, right? So for us, we basically swap out the OVS and we have completely replaced it with a programmable data plane. So there's a big difference in sort of OVS, which is a configurable virtual switch, and it's a fixed feature capability switch, versus something which can be, which is a programmable data plane and can actually be dynamically programmed and extended for capabilities. So we'll talk about that a bit. So the way the Hypervisor works is it's based on the code which we had from Multi-Hypervisor builders, which we extended it, and it's called the extended. It's called the eBPF, the extended Multi-Hypervisor builders. And what we do is we actually program this data plane with the functionalities of the various different virtual network functions as and when we need them in the data plane. So the data plane itself starts off being completely empty, and then as new services and features are required, the data plane component of those services is programmed into this Hypervisor. Remember, the Hypervisor was deployed on all the edges in the cluster. The edges is where the VMs are getting onboarded. The VMs with their virtual interfaces, those interfaces get onboarded onto the Hypervisor. So the same place where you have the OVS, you don't have the OVS, the Hypervisor is onboarding and all the interfaces. And inside that Hypervisor, we have it as a programmable framework, and we are able to instantiate multiple different virtual networking functions. The BPF reference which I made was the fact that when we actually program the Hypervisor, we actually download the code which gets compiled inside the kernel. There is a JIT compiler, which was there in BPF, which we have now extended with more capabilities. And those extensions, they allow us to have a very feature-rich classification capability for any of these components inside the Hypervisor. All right. So in terms of an architecture, from that point of view, we have the network functions, and they are split by control plane and their data plane components. It's only the data planes components which are set down and actually configured inside the Hypervisor. Right. Okay, so, and we'll come back to some of these concepts. As I said, I'm just trying to bring all the technology components together, and once the whole thing comes in, then you can figure out how they interact with each other a bit. So, the Hypervisor itself, being such a key component of the technology, I mean, we are a 4-year-old company which has been working on this particular platform. And this now, we just recently announced it as a project of the Linux Foundation. So the entire capability is available for everybody to sort of download and actually make use of. And it is available on GitHub, and you can sort of basically use it along with the SDKs and actually play with it in terms of trying to program some of these classification capabilities and being able to use them inside an Hypervisor on a data plane, right? Okay, so I'm going to come to this. So now let's talk about another key component, and I'm losing track of my, okay, is the virtual domains. So the Hypervisor is good. I mean, it's you know, all this extensible capability which we have, programmable and everything else. But then in terms of actual usability of networking fabric, right? What are sort of the key things which you have to have? If you think about the many different solutions out there which are about trying to create and stitch various different virtual machines together in different type of topologies and everything else, they focus more about how you can sort of automate that stitching and trying to establish all that connectivity, right? I mean, you've got frameworks which can go ahead and do the various different configurations. But very soon, when you start thinking about the network platform, which is sort of where you want to go and sort of try and scale this, where you will have 200 edges, 300 edges, and now you start thinking about the thousands of different virtual machines on that. Very soon, you will start come to this point where how do you sort of even try and visualize how those different virtual machines are talking to each other, and where is your network sort of segmentation and everything else, right? So OpenStack has a concept of projects, and within a project, you can obviously go ahead and create various different networks, which essentially is a bridge. And on those bridges, you can go ahead and sort of mount up the various different virtual machines. So what we have is this concept of virtual domains, which in the OpenStack world maps nicely to a project. And inside that virtual domain, think of it like a container of networking components. So the way we envision this is you can take whatever you want to call as a sort of a network, and you can put it into a virtual domain. And then you can have that virtual domain have its own sort of policies, its own sort of rules, its own sort of network topology, and then you can have it get deployed out onto the various different compute nodes in your cluster, right? So the way this sort of plays out, let's say you have virtual domain 1, and which is for the first tenant. So what we are offering you there is a way to kind of completely step away from all the issues around stitching and trying to bring the topology together, and just be able to view as to what is the type of network you want to deploy at a higher abstract level. So what you really go ahead and do is you say, like, look, I want a router, I want 2 bridges, and my different virtual machines inside this type of topology. There will be some machines which will show up on one bridge, some will show up on another bridge, and they will be connected together through this particular router in the middle, and then they may have an external load balancer, and then they are connected out to the internet, right? So that you sort of define as your virtual domain, and then you can go ahead and apply the virtual domain out into your cluster. Now, what does that mean? So what that translates to is, like, now I'm going to try and bring all these various different technology pieces together, right? So a virtual machine gets launched by Nova, and this virtual machine now ends up on, let's say, compute node A. Okay. Now on compute node A, this virtual machine shows up. We say that this virtual machine actually belongs to tenant 1. And we know that this machine now is going to be onboarded onto a bridge 1 of tenant 1, right? So at that point, what happens? At that point, on that edge, the director downloads the data plane component of that bridge into the hypervisor and says that, hey, hypervisor, here is a tenant, and for this tenant, we have a bridge, and on this bridge, we are now going to mount up the actual virtual machine. The dynamic programming happens at that time when the VM actually shows up on that particular edge. We have not gone ahead and proactively simply sort of configured the entire network with all the virtual domains and all the rules and everything else upfront. It's like happening as things are onboarded. Please.
So in the 1900s, I knew what a bridge was. What is a bridge for you guys?
So it's still a standard bridge, smart bridge. It's got some extensions on the way it sort of handles traffic for broadcast and multicast, but essentially it's still a standard layer 2 bridge. So it's same thing. It's a layer 2 bridge. And when you say router, it's still an L3 standard router, right? Okay, so now the thing happens that there is a second VM, which now Nova is going to try and launch, but it launches on a second edge, not on the same edge, right? Now, when this VM shows up, we figure out, oh, this VM also has the membership for the same bridge, which we already had on edge 1. So another instance of the data plane of that same bridge is instantiated inside the hypervisor of the second compute node. Okay? And it's a second instance of the data plane, but single instance in terms of control plane. And that control plane is sitting inside the directors, right? So the directors are hosting the control plane components, and the hypervisors are the place where the data plane components are being instantiated. So single bridge, but with 2 separate data planes. Now that these 2 separate data planes have been instantiated, now you say that, okay, they are the same data plane, so there is VXLAN tunnel which is established, and that's how these 2 data planes are now stitched together to create a single data plane bridge, which now is spanning across 2 different nodes, right? So design principles like these is what is helping us, from a platform, to be able to scale to very large type of installations, right? So this is not like, a set of scripts, as I said, put together to sort of simply create a 5-node or 50-node type of a cluster. This can actually scale. And if you think about it, why it can scale is because as you add more number of virtual machines, on any given node, maybe you will have virtual machines which belong to 5 tenants or maybe 7 tenants or whatever, right? So only the components required by those tenants actually get instantiated on that particular edge. So as you now keep on adding in more and more clusters, more and more compute nodes and more VMs, we can still continue on scale, right? So on that particular topology, you had a concept, let's say, of one bridge with 2 of the virtual machines, and then you also had a router there. So from a topology point of view, the directors are able to understand that, wait a bit, this traffic may actually want to go out to the internet through the router. We do not have a network node concept. Our entire data plane is fully distributed. So what does that mean? It means our router will have a control plane data plane select. The data plane of that router also gets instantiated onto each of these edges along with the bridge, because we know that the bridge is attached to a router. All right? And that, so now when the traffic is being forwarded out and there's a decision to be made whether it needs to be sent out through L3 services of a router, that decision is made on the edges itself, because the data plane of the router is on each of these edges. The control plane is still one. So if there are any routing updates and everything else, there is communication happening between the data plane and the control plane, which will keep the forwarding information inside the router data planes, inside the hypervisor, always updated in time. Right? So again, now when you have capabilities like NAT, NAT is also a distributed service for us. There isn't like any hairpinning type of a sort of a solution where all north-south traffic going out of a cluster has to end up onto a few set of network nodes, because you need to suddenly figure out, oh my God, how do we manage these IP tables? Not the IP tables, the IP pools for the traffic as it goes in and out, right? So the way we do that is by actually having sort of segmented out micro pools. And we have a very interesting architecture where the forwarding decisions and everything else can also be made completely independently on each and every edge. And it's just managed through the set of directors. The reason I keep calling them as directors and not controllers is because the traffic does not traverse through them. They are just there to basically go ahead and do the orchestration of these various different virtual networking functions onto the hypervisor edges. So even though they are already running in an HA type of a cluster configuration, obviously if one of them dies, the cluster is still up and running. 2 of them die, it can still continue. But all 3 can actually go away, and the traffic still continues, because it's not flowing through them. The only thing you obviously can't do is you cannot now create new tenants and new topologies, but your existing topologies and everything else will continue operating. So there is redundancy, and then on top of redundancy, there's more redundancy, and then there is full high availability. So multiple layers of trying to make sure that if the edges lose communication with the detectors, at least the ongoing program configurations will continue working. All right. So I think that if you guys have no questions on this, I think.
We have a question from
Oh, please.
online.
Oh, yes, please.
How to load balance the traffic in a virtual domain? What are the constraints? What all constraints should be taken into consideration?
Okay. So to load balance the traffic, now the NOVA scheduler is the one which is sort of through accelerometer and everything else monitoring how much is the load on the various different compute nodes. And the decision about for a virtual domain, how many virtual machines are supposed to show up on a particular edge is really made by the OpenStack orchestration NOVA drivers, right? So that makes sure that your virtual machines are simply spread out and distributed out across all the different edges. And for us, wherever that machine shows up, we go ahead and stitch in the different data planes, and we make that whole topology come up, and we create a VXLAN tunnel, and things are up and running. So we ourselves are not orchestrating and distributing out the virtual machines, and therefore not sort of trying to distribute the load of the VMs across the different edges, or influencing that in any particular way. Now, there is another aspect of the question. If that question was that how do you get a load balancer as a service, like a service insertion type of architecture, I think we can talk about that also. The Plumbed framework allows many different ways in which you can stitch services into the path of the traffic as it is going in and out of the virtual machines. One of them is, so actually on this particular topology, you see the things which are in purple are the ones which are native Plumbed functions. They are part of the network platform itself. The things in orange is what we have as third-party functions, right? So you have a load balancer in tenant A, which is in orange. And now the question is, how do you sort of integrate that? Now, this could be an F5 appliance or A10 appliance for that matter, right? Which is sitting outside because it's a physical appliance. And the way we are able to do this is we can stitch its interfaces into the particular virtual domain topology. And how does that happen? So a physical appliance has got interfaces. Those interfaces we are able to onboard into our platform. Once they are onboarded, they exist as connectors for us, right? There's traffic coming in and traffic going out. And those connectors, I can simply go ahead and stitch and say that the router on its north interface has one connector, and then the other connector is connected out to the internet, right? So what happens now is that the traffic which is going in and out of that particular virtual domain basically goes out, gets hairpinned out to the physical appliance, gets processed by the physical appliance, and then comes back into the virtual domain. So that's one way of doing service insertion. And by doing that, I mean, we can pretty much onboard any type of a physical appliance. If the appliances happen to be multi-tenants and everything else, instead of taking the whole physical interface and sucking it in, we can actually have VLANs out of that physical interface. And we can onboard one VLAN of one tenant and another VLAN of another tenant. So even though you've got one physical bus, I mean, you can definitely have a multi-user type of a configuration, which you can operate like that. So that is one way. The second is obviously is that many of these third-party functions now have virtual form factors. So you can simply spin it up as a virtual machine. And when you spin it up as a virtual machine, you spin it up with interfaces to two different bridges, and then you can actually insert that particular virtual machine in the path of the traffic. You can simply make sure that the traffic passes through one bridge which connects into the input interface of that virtual machine, and then the other one goes outside and it sort of shows on. In the demo which I've got, I do have some virtual machines which have been configured like this, where you can think of them as third-party virtualized network functions, and we can also talk about that. There are, please.
So for the physical integration, F5.
I know people are hearing you, but the hangout people can't hear you, so this helps.
So for the physical F5 and A10 integration, are you saying that you're able to talk to these devices on one interface and have VXLAN directly dominate on those devices?
So these devices, most of them don't have native Meetup sort of translation capabilities. They basically have VLANs. So you have a physical interface, you have VLANs, and what we are able to do is on, let's say, our x86 gateways, we are able to basically take each of these VLANs and have it come into our virtual topology as a separate interface. So each VLAN ends up as a separate interface for us.
Is there a native integration, or is it just a VLAN bridge to VXLAN integration?
So the workflow which I was describing is, let's say, for an F5 type of load balancer, which basically can be a multi-tenant type of load balancer, and it can be multi-tenant because it supports the tenants by separate VLANs, right? And then it's got IP pools and everything else, and they're configured by these separations of VLANs. And that was the workflow I was describing, that, hey, you can take a VLAN which belongs to tenant A and then make sure that it comes in and gets connected and is available in that flow path. The Meetup part which you're talking about is, let's say, we have integrations with the Meetup hardware type of switches, let's say the Arista switches or the Cumulus switches, right? Where we are able to integrate with those switches to a level where the Meetup endpoint actually becomes part of our fabric. And when it becomes part of a fabric, we are able to have a control plane communication between our director and the switches control plane, and figure out like what are the VLANs which it is trying to onboard on the other side and what networks they belong to. So we are able to, across the Meetup gateway, also stitch the VLANs on the other side into the virtual topologies. So if you go east-west, then like bare metal type of onboarding is possible, and if you go north-south, to the top of rack type of switch type of thing, we have that integration capability also, right? So that's where, so in terms of taking the VXLAN world into the VLAN world, you've got the x86 gateways, which is like a standard x86 box, or you can have these integrated type of boxes with the Arista or the Cumulus and stuff like that, and the ASR, the Cisco Nexus 9Ks.
Are there any performance considerations, or has there been any benchmarking done on the virtual domain performance?
Yeah, absolutely. We have our solutions deployed in some very large-scale production networks, and our customers are always wanting to sort of see what are the various different attributes they're always wanting to sort of see what performance they can get out of a solution. And at this particular point, we do have numbers, they are published, they are very, it's always basically goes back to, comparison of OVS versus an iWiser type of performance. And I can tell you that even though it's an apples and oranges type of comparison, because you're comparing switch versus a fully programmable distributed type of data plane. But if you talk about performance of a fully deployed sort of a topology where you want all these services to be distributed and everything else, we do come out way ahead. So from a whole solution point of view, because you have it scaled out, distributed across different edges. You've got all these capabilities of doing the gateway translations with all the various different manufacturers. Overall, you get a much better OpenStack solution performance as compared to just trying to do a comparison on raw performance. So there is a little bit of a trade-off on just doing comparison of simple packet forwarding and everything else. Though in that trade-off, I can tell you we are at par. So the thing is, I cannot sort of say that we get better because you really can't be. In the end of the day, you just start forwarding the packets as compared, in terms of RIOL solution or any other sort of a solution. But the place where the performance really starts coming into play is when you talk about multiple services, virtual domains which are complex with various different virtual functions integrated into it. There we come out way ahead.
You got it? But there's a question on the
I'll read it. What's that? This is from Sri online. If traffic is flowing from VM to physical device, and then from physical devices to VMs, what's doing the load balancing, and what's monitoring the load balancing to send the flow of traffic?
Is it the Nova schedule or is actually a specific question? What is actually?
I think that.
Yeah.
I edited that out.
Yeah, because if the answer is no, let's say no.
It's not the node schedule. There's load balancing separate.
You
See-
know, data plane load balancing, that's not the control plane. So Nova schedule is going to be for the control plane for the VM.
For the VM.
But I think the question is more about data plane.
Yeah, we need to put it specifically, so let's
So-
just tell no, it's not that.
Okay.
Someone in the microphone, because Shmi can't hear me shouting all the way to India.
Okay.
Just carry on.
All right. So I think so I just want to qualify this question. I mean, are we talking about load balancing of the load in terms of the virtual machine load across
That's
different
what it
edges?
seems to be.
That is obviously the Nova
That's
scheduler.
what I interpreted.
If you're talking about how does sort of the traffic get load balanced, and this is a typical sort of a use case where you have a pool of web servers and you've got traffic coming in from the outside and you want to distribute that traffic to this pool of web servers. And that's what the whole F5 example which we were just now talking about. And what I was saying is that that particular load balancing function would be part of the load balancer itself. And that's why we went into this details about whether it's an F5 or it's an A10 or whatever, what are the different ways in which you can integrate that particular load balancer into the into the virtual domain traffic flow, so that it distributes out to this pool of web servers, right? So we'll leave it at that unless he comes back with a
Yeah,
little bit
so
of
I have to
qualification on that.
verify that didn't make sense to him.
Okay,
I just had one more question.
sure.
This is in continuation of the entire load balancing discussion. In terms of the virtual load balancers like F5 or A10,
Yes.
how is the integration actually done? Does Neutron call your plugin and your plugin as an API call to F5 or A10 and instantiate the virtual machine?
Yeah.
Or is there a separate Neutron plugin that I directly use with F5 and then instantiate that somewhat plugin to the thing?
Okay, so we are a core plugin in OpenStack, right? We are a full platform, so we are not an ML2 plugin. So from that point of view, we do take over the entire, we take over servicing all the APIs within Neutron. Now, one of the integration models here is possible is that you spin up the VM from, let's say, in this case, F5 or a VM, and that has its own set of APIs, which are available as Neutron service extensions, right? And then what happens is that in terms of the orchestration framework which you have sitting on the outside, now that orchestration framework could be a set of Python scripts, or it could be some like each sort of template, right, or Murano sort of Murano type of a script. You could then go ahead and create a templated topology where you would say that, okay, I'm going to spin up I'm going to basically create the whole virtual domain and spin up the entire network, and here is the virtual function, A10, F5, whatever, which is also being spun up, and then using those APIs, stitch the interfaces of the VM into the topology, and then you use the extension APIs to actually program the virtual function itself. We do not program the F5 or the A10 in terms of its own configuration about how you need to sort of do its all the various different settings in terms of creating the pools and figuring out as to how the traffic is going to flow and everything else, right? We leave that to be kind of handled from an external orchestration thing. So what we do, sort of, as I said, within our set of APIs, allow you to stitch those interfaces which show up once that virtual machine is instantiated. We will go ahead and configure it into the topology, but in terms of the virtual function itself, whether it's a SSH connection into that virtual machine to sort of go configure it, or its own extended APIs through Neutron framework, all of that. All those options are open for sort of the outside orchestrator to actually manage. All right. So we do not take ownership of all the various virtual functions. That takes us away from our key focus, which is the network platform. Good. All right. That's it. Please, feel free to ask questions. Yes, please.
So back to the same load balancing point of view, the thing is in the way of, if I understood from the question, I think that is something, or maybe different question, more related to, let's say, in your tenant B,
Yeah.
you have one firewall.
Yeah.
And then because of the traffic demand, it's got another new firewall.
Yeah.
You have multiple firewalls.
Yes.
In your system, in your implementation, how did you provide the infrastructure load balancing? This is not about ADC or some other thing.
Okay.
This is when you have more than one firewall, how are you going to load balance those traffic?
Very good. So in terms of the purple items, we already discussed as to how those get load balanced, right? Because that we control, we have control between data plane separation, and we can instantiate those things. Now you're asking about a third-party virtual function, like that particular firewall, which you sort of inserted into the traffic path. And how does that particular appliance understand how to do load balancing? And there are different solutions from different vendors we've seen, right? So Palo Alto has a different type of a solution where they are able to spin up multiple different firewalls as sort of required as traffic starts scaling up, and they can still centrally manage it. But it all becomes very third-party partner sort of solution type of. It basically now depends on their capabilities. I mean, what I'm trying to say is that we don't sort of in any way have any limitations, but it's for them to sort of figure out how they will, instead of, let's say, having one single instance, they want now multiple instances, how will they will distribute their data plane instances out to handle all the traffic load.
Yeah, but I thought the VM is what responded, right? The system responded to one of the VM. So when you spawn those VM, when you have a multiple of those, you have traffic coming in, how do you, in your infrastructure layer, I'm talking about the virtual infrastructure layer, how you're going to
Okay. So one of the ways to do that would be basically to spin up a separate virtual domain, because, the virtual domain, which is essentially, as I said, it maps out to another, like an OpenStack project, because the type of a situation you're saying that we've got too many of these virtual machines inside a cluster, and too many of these virtual machines are now trying to access a particular service, and that service is getting overloaded. So that particular service, as it is not able to scale. Now, in the case of, as I said, any of the purple level items, we can scale. So you only have to, from the design point of view, only have to create one virtual domain and then keep on adding more and more machines to it, not a problem. But in this case, we have a third-party function which is now getting overwhelmed. And therefore, now we have to kind of see, okay, this third-party function can handle how many different virtual machine clients? We can handle 100. So if you want more than 100, it's time to spin up another project which maps to another virtual domain and have that same type of topology. And then after 100 machines, start basically attaching them to a different bridge and a different topology, and then scale up. That's one of the ways to scale. That's it. All right. Okay. So inside the Plum Grid Hypervisor, I mean, this is a quick sort of recap. I mean, I've been waving my hands in the air. So this is like how the virtual machines are now coming on to a particular edge. We have a function called PEM, which basically is the one which says, okay, here is a particular topology through which this traffic has to traverse. And essentially, the traffic traverses all the data plane components of that particular topology before it goes out onto the edge, right? So all your routing, NATing, forwarding type of decisions are all made off on the edge itself. And this is the key thing, right? Because all your networking decisions are now distributed out across all your edges. There's no sort of a central place where all the traffic has to sort of show up, and then we have a choking point, right? Okay. So again, just essentially around virtual domains. I mean, if you think about it, it basically is got all the capabilities of micro-segmentation. You can create virtual domains to be as small as a single virtual machine sitting on a single bridge with a single router and having connection to the Ethernet. It doesn't have to be 100 machines, right? It's just a construct about what you want to sort of have control over. And once you define that as a virtual domain, then all the policies and everything else which you want to sort of create in terms of the access it has got and what type of traffic it can sort of see and what type of connectivity it has, you're able to sort of have those have all of those policies basically get applied on that virtual domain. So when you're talking about these policies, right? For us, I mean, security is a very key focus in terms of trying to make a scalable type of an infrastructure. You really don't want to sort of try and have this concept of using IP tables on different nodes and then trying to figure out this IP table belongs to tenant 1 and it's his rule set which this is supposed to filter out, and then here comes tenant 2 and tenant 3, and very soon you have the same sort of core function which you're trying to use for security, which is not designed to sort of handle multi-tenancy. And forget about handling inside every tenant. You can have clusters of VMs, which may be because remember, a tenant could be a company, and then inside the company you've got engineering servers and marketing servers and everything else. And you are now trying to have rules by that type of sort of. I mean, you're trying to have rules which can classify the traffic and trying to keep it all separate. It very quickly becomes a mess trying to figure out what sort of policies and rules you actually applied into your entire cluster, right? So the way we kind of enforce security is on the edges of the VMs. So as the virtual machines are onboarded, their membership to a particular security group. Now we do have a concept of security groups, right? So I mean, you don't do ACLs, right? So ACLs is when you sort of simply have a set of rules which are going to be used to filter traffic versus a concept which is much more scalable after ACLs called security groups. And with security groups, what you do is it's a classification based on membership, right? So you basically end up where you can sort of say that all of these VMs belong to the engineering domain and all of these VMs belong to the marketing domain. And then all you have to do is to create one rule, which basically says that, okay, that the engineering and marketing can only communicate on port 80. So only a web server traffic can go in and out of it. And by the way, this rule was inside the tenant. This is not sort of an external rule like where you're sort of talking about access to the internet. This is within the tenant itself, you can have more of these complex rules. So we have sort of built out this whole security framework to be very extensible. And the main thing in security groups is that you get visibility into what actually is going on in terms of your security policy. Otherwise, I mean, if you start trying to read IP tables and trying to sort of make sense about what traffic is supposed to go and not supposed to go through it, you just are not able to do that. So that's about security groups. If you guys have questions. I'm going to take a time check. I'm already at 8, so I do want to spend some time with the actual demo and everything else because we really didn't hit the multi-hypervisor aspects of it yet. We are still on sort of the single hypervisors at this point. So in terms of the architecture, Neutron and Plum Grid, so it's very similar, except that we've taken we have taken care of all of the issues which were there in sort of the standard Neutron OpenStack type of an architecture, right? So I think that's what I was trying to explain and go through. And essentially, the whole thing. I mean, when we talk about SDN, I mean, SDN has evolved a lot from where it used to be this whole controller-based sort of a configuration of multiple data planes. And what we are saying is it's really evolved, where it's not a control of different sort of virtualized or even physical devices, but more about giving you this whole programmability, extensibility, and all of these capabilities, which is what we have with the Hypervisor framework. Yes, please.
Yes, Sriram's asking about a mixed hypervisor environment.
Yep.
Are there any Plum Grid capabilities rewired the network to assist with moving workload from one hypervisor environment to another, say from VMware environment to KVM on your network?
So good segue into sort of the multi-hypervisor networking architecture. So with that particular framework, how is it that we actually do multi-hypervisor, and what is the advantages of trying to sort of apply that? So I will come to that answer in a few minutes, right? So as we sort of walk about what is the demo. So the demo is going to be to spin up one of these virtual domain topologies. Now let's take a close look at this virtual domain topology. Slightly grainy, but so we take a look at tenant 1. Tenant 1 has internet access through a NAT, right? It's a standard sort of an OpenStack type topology. You've got a shared network going on, and then you've got you've got a provider network going on, and you've got a NAT instance in it, and then you've got a bridge, and then that you have a router, and that's connected to a bridge, and then on that first bridge, we are calling that the DMZ bridge, right? So we've got virtual machines which are instantiated on that particular bridge because we want to be able to give them floating IPs, right? Because they are in the DMZ, so they should be IP reachable and everything else, right? So they are there. And then we've got two other bridges. There's an engineering bridge, and then there's a sales bridge. And on those bridges, we've got other virtual machines which are below the DMZ. The icons which are slightly grayed out are essentially the VMs which actually are spawned on the VMware hypervisors. And the icons which are in normal green are on the KVM hypervisor. The orange icons, if you think about them, they are kind of like service insertion, right? Because I've actually inserted a virtual function which has got 2 legs in it. Think of that maybe like a Palo Alto firewall, essentially saying that, okay, hey, as the engineering traffic goes out into the DMZ, it needs to get filtered through a particular sort of through a firewall. And what we've done is we've actually deployed one of those on a ESX hypervisor and the other one on a KVM hypervisor, right? So we're going to try and do this, which is a true sort of a multi-hypervisor type of a deployment. You're not seeing me sort of call out which VM is around. I mean, you basically are not seeing me sort of say that, okay, here is a hypervisor cluster, here is a KVM cluster, and here is a VMware cluster, and look, now these clusters can sort of find talk to each other, right? We have got the same virtual domain concepts, the same level of security granularity which you had, which we've been talking about, right? For each and every sort of set of rules and everything which you can apply. The same rules are getting applied, and the VMs themselves are getting being spun up on different hypervisors. Now, why are these VMs being spun up on different hypervisors? Because you may have in your network a firewall which you only have a VMDK for, right? I mean, you don't have it as a KVM. And somehow the third-party vendor says that no, this hypervisor makes a lot of sense. I mean, this particular networking function makes a lot of sense only on a VMware hypervisor, right? You may have a Microsoft Exchange server or something like that, which only runs on a VMware hypervisor. So therefore, those particular virtual machines, when you spin them up, are going to pick and choose the hypervisor they want to go to based on the properties of those virtual machines. But you still want to be able to stitch those virtual machines back into the topology which you had designed from a networking point of view, right? So that's what I've got. I've got one orange virtual machine, which is a virtual machine on VMware. The other one is on ESX, and I've designed a topology where they will still, from all network connectivity point of view, going to come up together in one homogeneous network. So here's sort of the topology and the way this thing sort of the whole solution comes together. So now we essentially our networking platform integrates with many different OpenStack distributions. For this demo, I'm just using the Miranda's OpenStack. So what I have here is a Fuel node, which in the Miranda's OpenStack is sort of the node which goes ahead and actually configures all the hardware. And the Fuel node is going ahead and spinning up, let's say, three of the OpenStack controllers. It's spinning up 2 of the OpenStack compute nodes. And it is also going to spin up 2 additional compute nodes, which we are going to convert to our x86 gateways. Okay? So the way the whole solution comes together is that you basically stand up standard sort of an OpenStack cluster. Now, in that same data center, you also have a vCenter, and you also have its associated ESX nodes, right? So now you stand up a vCenter and the ESX nodes, and they are all now separate. Now, how the whole solution comes together is, what we do is, so we start off with, let's say, the Miranda's cluster installed, 3 controllers up, 2 computes, and another 2 more computes with the additional network interface, because we want to have internet sort of connectivity. And then you have the VMware installed. And what we basically do is we bootstrap the ESX environment. And what we do in this bootstrap option is that we spin up 2 virtual machines on the ESX nodes as compute nodes. All right? And these 2 virtual machines, when we spin them up, we pixie boot them from the same Fuel controller. So now, because you are doing a pixie boot of these VMs from the same Fuel controller, from Fuel's perspective, 2 more compute nodes have shown up in the network. All right? And these 2 compute nodes, which are now running on the ESX nodes, actually become our gateways to onboarding all the virtual machines which show up on the ESX nodes. Because these compute nodes have an iVisor inside it. And now, as the virtual machines are onboarded on the ESX nodes, right? So when a virtual machine gets launched on the ESX node, we are able to trap that interface. We are able to figure out that virtual machine belongs to which particular project, because that's like which basically maps to a virtual domain. We are able to figure out that interface, what bridge it needs to be connected to, and we are able to then stitch it into the virtual domain at the appropriate place. Yes, I mean, here you have to have questions, because this is.
So are you saying that all on ESX side, all user data is pushed to this other VM,
Yeah.
user space, and then goes
out to the interface. Yes.
What's the throughput on that?
Good question again there, too. I'll answer them one by one. So let's go for the first one. That is true. All the traffic, which basically is even going, let's say, virtual machine to virtual machine, basically gets directed in through the Hypervisor, which is running inside a VM at this particular point. Because the ESX hypervisor is a closed environment, we are not able to sort of put a module into that environment itself. So this is the next best thing, where you put a virtual machine on top of that, and you are now stitching all the traffic into your hypervisor, and then have it basically get forwarded into whichever path it wants to take. The virtual machine which we launch, we can actually use SRIOE, or we can use PCI pass-through, and we can actually talk directly to the NIC on that ESX node. That takes care of performance, at least going out of the node, right? Because you are not having to sort of, because that interface gets completely onboarded inside the edge which we have onboarded on the ESX node, right? So from that point, you have full performance in terms of talking to an outside interface, because you got the PCI pass-through. And with PCI pass-through, what we do is we actually take the fabric interface and we take ownership of the fabric interface to that VM. So now all you're doing is stitching in the virtual machine into the Hypervisor, which essentially is a memory sort of transfer of the information, because both of them are outside in the user space. So you have a packet which will go from the virtual machine, it will go into another virtual machine, and then from that virtual machine, it will go out to PCI pass-through onto into the fabric itself. Comparative performance as compared to a KVM sort of a solution, where you have a KVM hypervisor and you've got the Hypervisor running as a kernel module and everything else. It's lower, but with the PCI pass-through or an SRIOE type of integration, it's pretty decent. Now, what does that lower and decent really translate to? So say, for example, on a particular setup where we have, let's say, a VM or a KVM trying to sort of get external connectivity, a setup where you've got 10 big links and things like that, maybe you can get with full optimized VM workloads, maybe 2.5 to, let's say, 3 gig type of transfer rate out of that particular VM as it's trying to sort of have its traffic go out. With the PCI pass-through type of a solution, we've been able to hit on the same type of hardware around 1.8 to 1.9. So yes, we do have a 30% type of a performance hit there, but in terms of being able to get a solution where the networking and connectivity is all up and running and is all seamless, I think that is a price we end up paying, because that hypervisor is closed, right? But then again, as I said, this is the only solution out there which actually gives you neutron networking connectivity across different hypervisors. I mean, everything else out there, basically you end up with either a Nova networking solution, like the standard solution from Kubernetes itself out of the box is a Nova networking multi-hypervisor, where you actually stand these two things up as two separate entities and then just have interconnectivity and stuff. And as a result of that, things like security and all the various sort of fine-grained policies and everything else, those cannot be applied in the Nova networking world. I mean, Nova networking doesn't support security, so you can't do many different functions. So yeah, there's a cost, but I think we've been able to sort of actually minimize it to the extent possible, and at this particular point, I think it's an acceptable hit which we are seeing. So yeah, so in terms of the workflow itself, so we would basically bootstrap the ESXs, and then these nodes would be sort of seen as additional compute nodes. We would go ahead and deploy OpenStack on that. In terms of how we actually deploy PlumGrid, remember, PlumGrid is a full networking platform. So essentially, we just yank out the existing neutron connectivity and slide in our own neutron plugin, and essentially we are done at that point. Well, there is a little bit of code which needs to be transferred over to all the edges, which is essentially the Hypervisor code, because that code has to go in there. And along with that code, there is a little bit of helper functions, which are sort of communicating to the control plane and everything else, all that thing. So and the way we do that is we do that through LXC containers. Meaning we don't go ahead and start blindly deploying multiple packages on a operating system there, right? I mean, system administrators don't enjoy that, right? Where we suddenly are having to deploy multiple packages. So we keep everything of all our code and functionality is basically deployed as one LXC container and one kernel module for the Hypervisor. And that's how we can keep our code base separate, we can upgrade it separately, we can maintain it separately. It allows for a much more efficient type of an integration as we deploy the PlumGrid platform onto all the ESX nodes. All right, cool. So any questions on the sort of the technology side, anything there? Okay, now let's get into looking at this setup. So what I have here is, and you can see it. Okay, all right, good. So I'm just going to walk through my setup so that you can now map all those pieces you were sort of seeing in that topology diagram. Now, be mindful, my whole setup is fully virtualized. You know, it's virtualization thing after all. So I'm running in a single box. I'm running that entire topology which you just saw. All right. So how do I do that? Well, our good old KVM, right? So I've got my, I can forget the registers right now. I've got my compute nodes. Remember, there were 2 compute nodes. I've got my controllers, 1, 2, 3. I've got my fuel node. Remember, all of these were like sort of separate machines, really, right? And then I've got the other 2 compute nodes which are configured as my gateways. And then there's something called as LCM, which is a lifecycle manager, which is essentially our own code repository inside a setup. That's where we pull the LXCs from. And it is also a place where all the PlumGrid tools are deployed. And some of those tools really help you do quite a bit of the troubleshooting part of it, right? All this complexity which we have out there, it becomes very intense when you're trying to sort of figure out what issues are in it. And we've got some really cool ways of being able to figure out that and troubleshoot. So all of those tools, as of today, are sitting on the LCM. Eventually, they may just be on the fuel also. So that is the whole cluster on the side of KVM with Kubernetes and everything else. And then you've got the ESX cluster. So you've got the vCenter and you've got the ESX servers, right? So you've got 2 ESX servers and you've got the vCenter. And then you've got our fuel, and I'm sure that's timed out. So, okay. And so in the fuel, you can see the controllers, you can see your compute nodes, you can see that there are compute nodes which are coming in from the VMware side because they were launched and bootstrapped, right? So remember I was talking about the part about bootstrapping. So you see this is called PG Edge 1. Okay, you can kind of see it. So, and then you got PG Edge 2. So remember, these were the 2 VMs which actually have the Hypervisor inside it, and they were spun up, and they were spun up and pixie booted off the same fuel controller. So that's how they show up as compute nodes on the fuel controller. And then you've got the additional compute nodes which are there. I mean, so you got 2 regular compute nodes and you've got the 2 additional compute nodes for the gateways, right? So that's how you are able to sort of, from an OpenStack perspective, basically bring together, your ESX and your KVM edges. And now, when you take a look at, let's say, a network topology, and in this case, I just have a topology here where we've got, let's say, the thing for the internet, remember the topology? It was kind of split between the internet access, and then there was a DMZ, which is out here. There was a DMZ network. Now I'm trying to sort of map that virtual domain topology into your OpenStack sort of equivalent, right? So you got a DMZ, and then you got a sales network, and you got an engineering network, right? In OpenStack, all these networks show up as bridges. And on this thing, on the DMZ, say for example, you see these two different virtual machines. So there's a thing which we are calling as a web server, and maybe there's a file server, right? And these are sort of virtual machines which are there. Then you've got this, which is, think of this like inserted type of a virtual function, right? Because this is stitching your sales network to your DMZ network. And on this one, this is actually spawned off on the VMware on the VMware ESX node. So whereas here you have the one which is spawned on the KVM ESX, I mean on the KVM node, right? So you've got these different virtual machines being spawned either on a KVM node or on a VMware node, right? So if I was to simply go ahead and basically take this network offline, which is what I'm doing. So remember, there are many different ways of sort of trying to spin up these type of topologies. You can do it through heat templates, or you can sort of create some frameworks which basically make the neutron calls, right? And essentially, the thing which I'm just executing is simply a script which goes ahead and deletes and adds this whole topology, right? So, and as part of the script, what we have sort of designated is that a particular virtual machine needs to spin up on a KVM hypervisor, or a particular virtual machine needs to spin up on a ESX hypervisor, right? And once I sort of just go ahead and have this thing cleaned out, we will sort of walk through the workflow when we actually start creating the topology, and we will see how the virtual machines are actually being created and deleted. I don't know if you guys noticed out here on the vCenter, there were 3 more virtual machines which were there, which are not there right now. We just have the PGH1, PGH2. So the actual script is simply going ahead and deleting the networks and the virtual machines from the entire cluster. So you have this. So on the PlumGrid console, the way we have this is the full virtual domain view. It's going to timed out. It's just timed out on me. So here we go. Just a second there. My connections is all timed out. So while we were doing this thing. So anyway, I mean, we'll just come back to that. So we'll take a look at from here. I'm just going to go ahead and create that entire topology again through a scripted workflow. So we go ahead and start spinning up the tenants, which we have. So you see this place where a tenant virtual domain user configuration is coming in. We're going to create the DMZ subnet, and if we keep hitting refresh here, we will see that the networks are being spawned. So initially, just all the bridges and everything else get created. And we are trying to create that same topology which we saw earlier in the slides. So now we are spinning up the first router, which is going to connect between the internet, and the DMZ. So just waiting for that to get spun up. So again, as I said, this is on my one single machine type of a setup. So it does tend to get a little bit flaky once in a while, but I'm sure we'll be able to show everything. So let's just go to that. And here we go. So let's connect. So we're logging in into the PlumGrid console. Spun up. And of course, you can never get the passwords right. So podiums are not designed for typing. Okay. So in terms of the topology which you have on the PlumGrid side, right? I mean, from our view of the world, which is the networking centric view, we see that all the different nodes are up and running. We've got the 3 directors which are running on those 3 different nodes. We've got the 2 additional gateways. And we also have the ESX nodes as part of these other compute nodes which are up here. Now here, this thing, as it is spinning up, you are actually able to see the topologies being spun up. So here is our service domain, and here is the tenant, the NFV tenant which we had, and here is sort of the different networks which we were creating. Remember, this was the DMZ network, and the virtual machines are hanging off here. This is the sales network here, and this is the engineering network here with its own DHCP instances and everything else. Again, this is a full-fledged platform. So what it means is you can actually go in and you can actually edit and see various different configurations which have happened on these VNF functions, right? I mean, this is a router. So you generally expect to see things on a router in terms of, let's say, some stats about, you know, what are the various different IP subnets which this router is seeing. I'm sorry, you have a question, please.
Can you see on the PlumGrid interface how the PlumGrid virtual domains are mapping to the Nova compute nodes?
Yes, you are able to see that through 2 different sort of modes. One is when you click on sort of the various on the VM Explorer, you're able to see all the interfaces which have been onboarded, which belong to the different virtual machines, and the mapping of those interfaces to the various different bridges. So you can see it like that. Now, in terms of a visualization, we did have this thing where, you know, each and every virtual machine would sort of show up separately. But as you go into sort of very high density type of environments, it becomes very maddening to sort of see all those things, and it becomes a clutter. So what we end up showing them all is inside this sort of a group like this. Like, you know, this is the virtual, these are all the machines hanging off this particular bridge. Here are the virtual machines hanging off this particular bridge. And then you can kind of see. And here what you're seeing is them, they are all obviously separated out by the tenant. So what we did is we only spun up one tenant. So this is the NFV tenant. And for that tenant, here is the topology equivalent of what you see in the OpenStack side, right? So you see the DMZ network. So here is the DMZ bridge. You see the sales network. Here's the sales bridge. You see the engineering. Here's the engineering bridge, right? So that's how that whole configuration sort of maps out. Okay. Now, we had this thing. We had this script spin up the topology, and we wanted it to spin up machines on the VMware side, because remember, some of those were actual VMware VMDKs. So they were spun up on the ESX nodes. So you see these additional images, and here you have the other one. So from here itself, you can now go in. Let's say this is the way it's the nomenclature is. It's VC, meaning it's a VMware client. So I can open a console to the VMware client. It's a Ceros image operating out there, and it's got its IP address, and we can basically try a ping test to the internet connectivity from this setup, and that may not work on this particular setup of mine, but it did get an IP, so we just allow it to continue here. And let's see another one, which is a machine on the KVM side, which I'm going to open a console to, and let's go in there and side to communicate. So I'm able to connect out from that. This particular thing is, for some reason, it's timed out, but I can try and troubleshoot it after this one. So not a problem. So you get, yeah, so that's essentially from a demo point of view, trying to show how you can take a topology and you can spin it up, whether it's got KVM nodes in it, whether it's got VMware nodes in it, it doesn't really matter. The Nova scheduler takes care of figuring out where that node needs to spin up. We have the Hypervisor edge running on all the ESX nodes. It figures out the same way as it figures out on a KVM edge that here is a new VM. It needs to be onboarded onto a particular bridge, onto a particular topology. The scale out which we have on the KVM nodes, it's the same scale out which we have now on the ESX nodes, because if you've got multiple different ESX nodes, you will have multiple different Hypervisors per node. As more virtual machines will show up, all the forwarding rules, everything else gets automatically pushed into the Hypervisors of those ESX nodes. In terms of adding new functionality, if you want more capabilities to be programmed into the Hypervisor and everything else, all of that flexibility which you get from a programmable data plane, we are able to extend that out onto ESX hypervisor also, right? Please.
Are you thinking of any other hypervisor support?
Yes. So I'll be thinking of any other hypervisor supports. So at this point, hypervisors, you can think of them as LXC itself, can be one type of hypervisor, or Docker containers, or essentially Hyper-V, right? So
webinars and so in few of our webinars and tour sessions, we showed the same thing, having the containers also working in the same type of environment.
So you're not considering Hyper-V?
No.
It can be theoretically done, but
So,
I don't think we can discuss more about it.
So it's not only theoretical, actually. I mean, to that answer thing, we do have the prototype thing. The theoretical part is about the interest and in terms of our customers who basically coming up and paying us to actually do that, right? We are, at the end of the day, a startup, and we are motivated by business cases. So in terms of capabilities and stuff for Hyper-V, there is a slightly different way in which you can actually do the integration, and we do it through extensions, because when you Hyper-V on the switch, there is an extension framework. And what we are able to do there is actually hook in the Hypervisor functionality into that extension thing itself. So we have prototypes of that, but at this particular point, now see as a business case to sort of actually go on that path. So that is there. To the leader's point on the thing about Docker, yes, if you think about it, what is a Docker? In the end of the day, it's a container which essentially has an Ethernet interface, right? And that interface is what you have to stitch into the right domain and the topology. And if that contextual information is available, you can easily spin it up. Now, in this particular space, from a networking point of view, we are ready. What is not ready yet is how to Dockers understand project names in OpenStack and figure out which is the bridge on which they want to spin up. How do they figure out that what is the IP addressing which is going on that bridge already versus trying to force their own IP addressing into the thing. So these worlds are still coming together. So as they come together and as those sort of solutions are actually created from a platform point of view, because we sort of created this whole sort of framework all completely thought through, we are completely ready to onboard those interfaces as usual with the correct classification.
Thanks.
So one question about containers. When you said that if an OpenStack is not ready for consuming containers in the way that you expect them to, but let's say not just with OpenStack, can you really can containers really consume security groups or some sort of hardware functionality that you guys have, NAT functionality, DNC functionality, or I mean probably not DNC functionality, but are you talking about containers which are on bare metal, or are you talking about containers in a VM, or what's the context right here?
So actually, both. We do have the bare metal integrations also. Again, if you think about how that would happen, right? So you have a bare metal framework. I mean, you have the node, which is not running OpenStack per se, but it's still got the iVisor on it, right? And the iVisor is the way we can stitch something into the network platform. Now, the only thing which is needed is that when you spin up that particular container, are you able to provide the information about that particular interface which that container has? Because at the end of the day, everything will have some sort of network interface. Whether that particular interface belongs to which particular bridge, which particular tenant.
One IO-visor assume that responsibility?
IO-visor will definitely assume the responsibility of the
Figuring out what bridge it is and where does the container connect to.
It will definitely assume the responsibility of figuring it out. But where are you going to set it? Somewhere it needs to be set.
So are you saying that we need to use another vSwitch for that? Another sort of
No.
Where does the container connect?
So the container in terms of network interface, sorry, you want to say something?
Yeah, I just want to say, as you're talking about IOI, I would like to mention like IOI is not provided within the project. So you may want to go on there and we have a full use case study and white paper in regards to how networking can be very. There is a whole white paper overview, get a project, so you can go into the examples like how people are building all that stuff. So we can definitely go down the path, but I'll go ahead and continue. Sorry. Okay. Thanks a lot. So how is it that in the VMware side of the house, we are actually figuring out where this particular VM actually needs to be onboarded? So remember when Nova actually launches that particular VM, it actually identifies that here are the interfaces for the VM, and it actually classifies, actually tags those interfaces with the information of that this interface belongs to bridge 1 and this interface belongs to bridge 2. That tagging information is what we use, and we go ahead and program our platform upfront. Now, when that VM actually gets launched, wherever it gets launched, I have the classification rules to figure out that, hey, this particular VM with this classification criteria needs to be stitched onto a particular bridge in a particular topology. But that rule was set by the end user, right? The OpenStack user, who sort of said that I'm going to launch a VM on this bridge. So in the Docker example which I was talking about, there has to be somebody who actually sets that rule and says that, hey, if you're trying to sort of onboard a Docker container on this type of solution, you have to be able to say that this container needs to be stitched and onboarded onto this particular tenant and on this particular bridge, right? And that information has to be tagged somewhere. Once it gets tagged, then for us, wherever that container shows up, doesn't matter because it will have that information and we can classify and onboard it into the right virtual domain at that time. So it's that stitching part which I'm talking about, right? If you take a Kubernetes sort of framework, do they actually share? Now we will see that thing happening as they sort of integrated, and then you will have the same keystone
database being used and the same user entities and the same project entities being used, then all this becomes very feasible because you launch a Docker container, you say it's supposed to be onto this particular bridge. We'll have the information classified, and for us, from a networking fabric point of view, we'll automatically respond.
Continuing on that line of thought, who do you foresee coming up with this integration? Is it a limitation of Docker, or is it something that OpenStack needs to integrate, or is it something that PlumGrid you guys can even just work around and create yourself?
So I think in terms of solutions to sort of explore and sort of create demos around, that's the beauty about the DevOps frameworks which we've got, that you can always create infrastructure and be able to create these type of solutions. But in terms of sort of actually creating them in a fully prioritized sort of form and scalable form and everything else, you kind of have to see how the solution will track.
So in our case, like we have one of our senior so he's working in the community itself in OpenStack to bring all this and he's actively participating in this type of environment for containers and Dockers and OpenStack. So you can check what's happening. What's the name of the project?
So Murano is the orchestration thing.
So he's
So,
working with that, so you can check and you can directly contact him and get his stuff.
Are you guys working on resource or?
I think I can disclose. So, Steve's question again is, I was unable to hear an answer from, just want to know how Nova schedule does this load balancing job. When we speak about load balancing, when it comes to my mind is traffic scheduling and the bandwidth. Is there any constraint that has to be considered? So
I think we're talking about virtual machines taking up bandwidth again. So it goes back to Celometer, where Celometer has a capability of also taking into account the networking traffic on a particular interface on a particular edge. Okay.
So the answer, Shri, in our case would be like it will be the VM load balancing and the traffic associated will be through the Celometer.
Yes.
Actually, this question is completely off topic into what you guys are discussing. Talking about reverse scheduling. You guys have got nothing to do with reverse scheduling.
So you want
Yeah. We don't have anything to Nova scheduling. The only thing which influences Nova scheduling is Celometer stats. Celometer stats do take into account the network traffic. So there is a little bit of an influence there that if a particular node happens to be sort of choked up, you can kind of influence the scheduler. Hey, yes, you've got enough of memory, you've got enough of compute, but you may not have enough of network bandwidth.
So that is more to do with where I launch virtual machine.
Absolutely.
Which is completely different than what you're talking about, which is load balancing data plane traffic versus load balancing scheduling traffic, which is completely off topic.
Thanks for answering. Okay. Anything else, guys? Thank you.
Please. Okay. Thank you. Next time.
Thanks, everybody. Thanks once again to our awesome presenters, Sharad and Dhiraj. And Amit was here for a couple seconds, and I was going to introduce him because he's going to be your next presenter, but I think he took off. He was the young man sitting there in the kingdom shirt. So come back on October 1st for a follow-up to our fabulous networking month as we go into NFV and carrier-grade OpenStack. So thanks so much again for PlumGrid and for the team for coming. Thank you so much to Alina and Sylvia. They're around here somewhere. They do it all for you. And, oh, there they are. You want to Alina? Come here. This is long overdue, but Alina's birthday was a month ago. And we did have some cake and things for her. The cake might have said it was Zach's 5th birthday, but it was really for Alina. But you have signed a card to you. So happy birthday. Really belated, but we did start that process. Sean even signed it, so you know I've been carrying this around for a while. So we're all huge fans of the Hangouts. And thank you so much, Rick, for doing the Hangouts and for doing this every single week.